Hello everyone and welcome back to the BEILab channel. Today, we will learn about spatial attention mechanisms, a fascinating aspect of deep learning for geospatial tasks. In this video, we will explore both the theoretical and practical aspects of spatial attention and Convolutional Block Attention Module or CBAM. But before we start, if you haven't subscribed yet, make sure to hit that subscribe button and give this video a thumbs up. Your support keeps us motivated to bring you more insightful content. Now, let's get started. Spatial attention serves as a computational module designed to enrich the effectiveness of learned features in a deep learning network. It accepts any intermediate feature tensor X as input and produces an enhanced tensor Y with improved representations. To provide a clear understanding of spatial channel attention, let's begin by revisiting channel attention in CBAM, a widely employed technique in convolutional neural networks. In this section, we begin by explaining both the channel attention module and the spatial attention module utilized in CBAM. Imagine we have the input tensor X with the shape of H, W, and C, where C, H, and W represent the number of channels, height, and width of the feature map, respectively. The channel attention weight in CBAM can be described by this equation, where WC represents the channel attention weight, sigma is the sigmoid activation function, ReLU is an activation function, and W1C and W0C are weight matrices. GAPC and GMPC denote the global average pooling function and global max pooling function of the channel, respectively. Similarly, the spatial attention weight in CBAM can be expressed by this equation. Here, Con 7 by 7 denotes a convolution operation with a filter size of 7, the bracket represents tensor concatenation, and GAPS and GMPS represent global average pooling and global max pooling functions of the channel, respectively. Although CBAM is widely used in convolutional neural networks and has demonstrated efficiency, it compresses the channel dimension C into a single channel to extract crucial spatial information and compresses the spatial dimensions H and W into a single pixel to obtain channel importance. This approach overlooks the interaction between spatial and channel dimensions. Now that we've explored the intricacies of spatial attention and CBAM, let's begin the implementation process of spatial attention. In the first step, we import essential modules from Tensorflow. These modules are fundamental for constructing neural networks, particularly convolutional neural networks, CNNs, widely used for vision tasks. From tensorflow.keras.layers, we import the following layers. We begin with the input layer, which allows us to define the input shape of the data. Next, the conv2D layer is crucial for performing 2D convolution operations. Additionally, the global average pooling 2D layer plays a key role in aggregating spatial information across the entire input, typically used for downsampling feature maps. Finally, the dense layer, often employed in the final stages of neural networks for classification, learns patterns in the feature space. In the next step, the provided code snippet implements a spatial attention mechanism using TensorFlow and Keras. Let's break down each component and its functionality. The spatial_attention function defines the spatial attention mechanism. This function takes an input tensor representing feature maps from convolutional layers. It first computes average and max pooling operations along the channel dimension using TensorFlow's reduce_mean and reduce_max functions, respectively. These operations aim to capture both global and local spatial information within the feature maps. The pooled feature maps are then concatenated along the channel dimension using the concatenate layer from Keras, creating a tensor with double the number of channels. Subsequently, a 1x1 convolutional layer is applied to the concatenated feature maps. This convolutional layer serves as a learnable mechanism to capture relationships between features across channels. Finally, a sigmoid activation function is applied to the output of the convolutional layer to normalize the values between 0 and 1, representing attention weights. The attention weights are then element-wise multiplied with the input tensor, emphasizing informative regions while suppressing less relevant areas. Next, the create_spatial_attention_model function constructs a neural network model that integrates the spatial attention mechanism. This function takes input underscore shape and number underscore classes as arguments, representing the input image dimensions and the number of output classes, respectively. Inside the function, an input tensor is first defined using the input layer from Keras. Subsequently, the input tensor undergoes a series of convolutional layers, interspersed with spatial attention layers created using the previously defined spatial underscore attention function. These convolutional layers apply various filters to extract hierarchical features from the input image. After the convolutional layers, a global average pooling layer is applied to aggregate spatial information across the feature maps. Finally, a fully connected layer with softmax activation is added to perform classification based on the extracted features. The model is instantiated using the Keras model class, specifying the inputs and outputs. Finally, example usage demonstrates how to apply the create underscore spatial underscore attention underscore model function. It sets the input underscore shape parameter to 224, 224, and 12, indicating an input image size of 224 by 224 pixels with 12 channels. The number underscore classes parameter is set to 10, indicating 10 output classes for a classification task. The function creates a neural network model with the specified architecture and displays a summary of the model, including the layer names, output shapes, and the number of trainable parameters. Now, let's shift our attention to the CBAM block. Similar to the spatial attention mechanism, the first step involves importing essential tools from Tensorflow. In the next section, the channel attention function takes an input tensor representing feature maps from convolutional layers and a reduction ratio R as input. Then, average pooling and max pooling operations are performed along the spatial dimensions, height and width, of the input tensor using Tensorflow's reduce underscore mean and reduce underscore max functions, respectively. Two dense layers, dense 1 and dense 2, are applied to the pooled features to capture channel-wise relationships. Then, the outputs of the dense layers are added element-wise and passed through a sigmoid activation function to obtain channel attention weights. Finally, the attention weights are multiplied element-wise with the input tensor to emphasize informative channels while suppressing less relevant ones. The next function is called the spatial function and computes the spatial attention mechanism. It takes an input tensor representing feature maps from convolutional layers and a kernel size of Ks as input. Average pooling and max pooling operations are performed along the channel dimension of the input tensor to capture spatial information. The pooled features are concatenated along the channel dimension and pass through a 2D convolutional layer with a sigmoid activation function to obtain spatial attention weights. The attention weights are multiplied element-wise with the input tensor to highlight informative spatial regions. Now, the CBAM function integrates both channel and spatial attention mechanisms to enhance feature representation. It takes an input tensor, kernel size of Ks, and reduction ratio of R as input. Channel attention is computed using the channel function, followed by spatial attention using the spatial function. The output of the spatial attention mechanism is added to the channel attention output using the add layer from Keras. Finally, the resulting tensor is passed through a relo activation function to obtain enhanced feature representation. Next, the create underscore CBAM underscore model function creates a CNN model incorporating the CBAM mechanism. It starts by defining an input tensor using the Keras input layer and passes it through convolutional layers, with each followed by a CBAM block created using the CBAM function. These CBAM blocks enrich the feature representations by selectively focusing on informative channels and spatial regions. After the convolutional layers, a global average pooling layer aggregates spatial information across feature maps, followed by a fully connected layer with softmax activation for classification. The model is instantiated using the Keras model class, specifying the inputs and outputs. Finally, the example usage section demonstrates how to utilize the create underscore CBAM underscore model function to create a CBAM-based CNN model. It specifies the input shape of 224 by 224 pixels with 12 channels and 10 classes. The function creates a neural network model with CBAM enhanced feature representations and displays a model summary, including the layer names, output shapes, and the number of trainable parameters. Thank you for joining us on this insightful journey into spatial attention mechanisms. Stay tuned for our next video where we will delve into the self-attention mechanism in vision transformers with code implementations. You can find the code examples on our GitHub page, so be sure to check it out. If you have any questions or topics you'd like us to cover in future videos, please leave them in the comments below. Don't forget to like and subscribe for more cutting-edge geospatial content, and we look forward to seeing you in the next video.